I'm going to go over the unit test. I'm just going to use Mr. Ku's answers here and just try to do my thinking as I go through. So the first question says here, consider the following concentration versus time graph. Which of the following reasons provides the strongest evidence that the equation for the reaction is 3A plus B turns into C and 3D? So I'm going to go through just each question. I say, okay, so B ran out faster than A. That doesn't make sense because it used 3 A's for every B. Okay, so, we're not going to use up the B first, so the A doesn't even make sense. Neither graph for A is linear. Okay, well, these are concentration versus time. The fact that they're not linear, okay, that doesn't really tell. It tells us something about the order. We know that this is not a zero order reaction, but that doesn't help us with the fact that, that goes with this equation. So we'll eliminate that one. The initial concentration of A is 3 times greater than the initial concentration of B. This equation only tells you about the change. It doesn't tell you about the starting amounts. You could start with the same amounts. You could start with lots of B and very little A. That doesn't tell you anything, so C is not useful either. The initial slope of A is 3 times greater than the initial slope of B. That is the right answer, and the reason is because we're talking about the change, the rate of change. A is going to change 3 times faster than B, so its slope is going to be 3 times larger than B. So D, that's why this guy is the answer. So the slope is an indication of the change. For number 2, the reaction 3 O2s turn into 2 O3s. The rate at which the oxygen is disappearing is 0.6. So this guy is changing at 0.6. So what's the rate at which the O3 is appearing? Well, you can see it's a 3-to-2 ratio. So O3 is going to change 2/3 as fast as the O2 is going to change. So instead of 0.6, it's going to change 0.4. That's that answer. Now, if I were trying to do this mathematically, I would say divide by 3, multiply by 2. And I can see that that's going to go in 0.2. So 0.2 times 2 is going to be 0.4. That's my answer. For number 3, okay, we have an equation. We have a rate law, first order. In an experiment in which X and Y are both 0.1 molar, so X concentration and Y concentration both 0.1 molar, the initial rate was found to be R. In which of the following initial concentrations will the rate be 2R, double that? Okay, so what we're going to do is just going to plug and chug. So on letter A, if I had 0.1, that's not changing at all. We're starting with 0.1. But this guy goes up 0.4, then we would expect our rate to go up 4 times. So A is not the answer. Okay, 0.2 and 0.2, we double the first one, that would double the rate. We double that one, that would double the rate again. So we get quadruple the answer. So that's not going to double the rate, that's going to quadruple the rate. Okay, if this one is 4 times, that would be 4 times the rate, but this is only half as much, so it'd be half of 4 times, that would be 2 times, so that's the answer. And let's double check. The last one is if this would be 4 times the rate, and that would double the rate, so we'd expect that to come out 8 times the rate, so we can eliminate D as well. So we know the answer is C. 4, consider the following data. So this is like a standard kind of reaction. What's the rate law? Well, obviously we'll start with here. So if we say O2 is not changing, so any change in the rate must be due to the NO. So the NO from 1 to 2, that's times 2, it doubles. And the rate, 5 and 10, we can see that that doubles. So if the concentration doubles and the rate doubles, then it must be first order with respect to NO. So that part's okay. Now let's pick 2 different ones. Let's pick these guys. What happens here is the NO is doubling, so we would expect that to double our rate. And the O2 is doubling. And so the rate is doubling, okay? So the rate is doubling, but we know the change in the NO is going to cause that to double. That means that this change in the O2 has no effect on the rate. So it must be 0 order. So that's why the answer is A. So as soon as we found that NO is the first order, we know we can eliminate B and we can eliminate D. So the question is the O2 first order or 0 order? And we can see what happens here is that it's got to be 0 order. Okay, for number 5, the decomposition of ammonia is a zero-order reaction. Zero-order reaction. So what that means is if we had rate equals K times the concentration of NH3 to the zero order, so what that really means is that is going to just turn into 1. So rate equals K. So we say, what's the value of K? Well, that's just the rate. We just have to find the rate of the reaction in terms of ammonia. Now the problem here is they're saying, okay, 0.05 moles of N2 is produced in 40 minutes. So the rate at which the nitrogen is forming is 0.05 divided by 40 minutes. Okay, and that would come out to be 0.0125. But we're talking about the ammonia. Okay, and the ammonia, since it's a 2-to-1 ratio, it's going to be changing twice as fast. So the answer is 0.00250 moles per liter per minute. So the ammonia is going to change twice as fast as the nitrogen is. Okay, number 6. An experiment was carried out to find the kinetics of the following reaction. The data was collected and plotted, and it was found that the natural log of C, okay, versus time is a linear graph. Well, there's a big clue. Okay, so if we're getting natural log of C versus time, then we know that if that's linear, this must be a first-order reaction. Okay, so what can we say? Which of the following is true? The graph of C, concentration of C versus time is linear. No, that would be true if it was zero order, but we know it's first order. The half-life of the reaction is constant throughout the experiment. Okay, that is a little tidbit. You know, when it's a first-order reaction, the half-life is constant. It does not depend on the concentration. So that's true. That's the answer. Let's try C. The rate determining step for the reaction could be 2C equals E. No, that couldn't be, because if it was 2 C's in the rate determining step, it would be second order. So that can't be right. And the rate of the reaction is constant throughout the experiment. No, that's the definition of zero order. Okay, that's the same, actually the same exact as step A. So that's not true. The only one that's good is answer B. Number 7. Which of the following could describe this graph? Okay, here's our reaction. Okay, the kinetics graph is shown. We got a straight line. Okay, so in its first order, there's an important piece. First order. So the concentration versus time, okay, would that be a straight line? No, not at all. Okay, because if it was zero order, that would be true. But since it says it's first order, then that would not be true. It would be a curve. The natural log of SO2Cl2 is versus time. Yes. Okay, first order, natural log versus time, that would be true. Okay, the ln of K versus 1 over time, that is a little bit tricky, okay, because if we had ln of K versus 1 over the temperature, that would be a straight line, but this says time, so that's not going to be true. And that would be like a inverse of the this equation. And the rate of SO2Cl2 versus the concentration, you know, as the concentration of our reactant increases, our rate would also increase. So we would get a line that goes up like that. So that can't be this one either. So it can only be answer B. For number 8, an experiment for the reaction A turns into B was performed, and the time at various concentration was recorded, which is the likely rate law. So we're really saying, is it zero order, first order, second order, or third order? Well, here we go from 1 molar to 0.5 molar, and remember this was a mistake on the practice test. Okay, it came out as 0.1 molar as a typo. So it's really 1 molar. So it goes down to half of its concentration in about 10 seconds. And then it goes from 0.5 to 0.25, about half the concentration in about 10 seconds. And then again, it goes down about half the concentration in about 10 seconds. So every half-life is constant. And remember, okay, half-life is constant in a first-order reaction. So the answer is B, first order. Okay, number 9. A 3% solution of peroxide is placed in beaker A, and a 30% solution is placed in beaker B, both at the same temperature. Same temperature, that's kind of important. When equal amounts of Ki is added, the reaction in beaker B proceeds noticeably faster than that in beaker A. Okay, so beaker B is 30% peroxide, and beaker A is 3% peroxide. Okay, this is A and this is B. We add the same amount of Ki to both, and B reacts a whole lot faster. Okay, so which of the following accounts? The concentration of H2O in beaker B is greater, so beaker B has more effective collisions than beaker A. That sounds true. Let's check the other answers. There's more Ki in beaker B. No, that's not true because they said they put the same amount in each one. The Ki in beaker B is an inhibitor, slowing down the reaction. There's no reason to think that. Okay, if it's going to do the same thing in both of them, it would inhibit both. The molecules in beaker B are moving faster. No, because it said the same temperature. So if it's the same temperature, then they are not moving faster. So it's a concentration effect, 30% peroxide versus 3% peroxide. For number 10, the following reaction is sped up by the presence of platinum. Okay, which of the following is true about this reaction? Well, platinum is a catalyst, okay, and platinum works because of the surface, and so things come and adhere to the surface, like we saw this in our movie, the chem study movie. So which of the following is true about this reaction? Platinum is an acid-base catalyst, allowing rapid transfer of hydrogen. No, it's not an acid-base catalyst, it's a surface. Platinum is in excess, but will eventually get used up. No, platinum's a catalyst, it's not going to get used up. The presence of platinum provides a reaction pathway with an activation energy lower than that without platinum. Okay, that is true because it's a catalyst. It works by lowering the activation energy. And the presence of platinum lowers the value of the rate constant? No, it doesn't. Okay, the rate constant, if it speeds it up, the rate constant might actually even get larger. Okay, but I mean, because it changes the rate, so temperature and the catalyst, those would change constant. But it's not going to lower the value, it would increase the value. Okay, number 11. The potential energy graph for the various conformations of butane are shown. The x-axis represents the torsional angle, or the angle between the near and far methyl groups. Okay, you say, what are we talking about? Okay, we're talking about if we had two carbons connected, then, we could rotate these atoms here so they could be hydrogen, hydrogen, and hydrogen. But we're saying one of these has a methyl group and the other one has a methyl group. And that these guys are large enough so they're going to kind of interfere with each other. So as this rotates around, okay, this angle here, then, what happens to the potential energy? But the real question is, what is potential energy telling us? Potential energy tells us the stability. So the lower the potential energy, the more stable the situation. And it looks like when these are at 180 degrees, when, one of these is here and one of these is here, opposite sides, that is the most stable. And that just makes sense because, they're big, they're going to get out of each other's way the best when they're opposite each other. And that'll be the answer. Okay, number 12. The Maxwell-Boltzmann distributions for two samples of a reaction mixture. So we're supposed to know that, this is kinetic energy going this direction. It's a sideways graph. And this is the number of molecules on this side. So which of the following is true? Okay, the reaction proceeds faster in T2 because more molecules are colliding with sufficient kinetic energy. That's the answer. Okay, because we're saying is that more particles, here's our threshold energy, more particles have enough energy to react in T2 because they have a greater average kinetic energy. For B, the reaction proceeds faster in T2, and that's okay, because a catalyst is added. No catalyst is added. If a catalyst was added, this part would be over a little bit, so the transitions, threshold energy would be lower than it is if there was a catalyst, and that's not true. The reaction proceeds faster in T1. No, that's not true. And T1 is not true. Reading really carefully again, the reaction proceeds faster in T1 because there are more molecules in that sample. Okay, both of these, it's a Boltzmann distribution. It's just a distribution. So the area under the curve is the amount of chemicals. And if we got the area under the curve in both of these graphs, we'd find out that it's the same. So that's why that's not true. And D, the reaction proceeds faster in T1 because it's got a higher activation, a higher average kinetic energy. T1 is taller. Okay, that doesn't mean that the energy is not up and down. The energy is sideways. So just taller means there's more particles on the low end of the energy scale than at the high end. So that's just not even true. Okay, 13. Consider the following Arrhenius equation graphs for two experiments. Which is true? The reaction in experiment 1 was faster because a catalyst was added. Okay, experiment 1, what do we know? We know that the slope is equal to negative E sub A, activation energy, over R. So this guy here has a smaller negative slope. That means it must have a smaller activation energy. And smaller activation energy means it is going to be faster. So experiment 1 is faster, and it has a catalyst added. Well, it definitely is going to be faster. That part's okay. We don't really know that there was a catalyst added. Let's check the other answers. The reaction in experiment 1 is faster because it took place at a higher temperature. No. Okay, this whole thing here, is different temperatures, and we're talking about K's at different temperatures. No, it's not the reaction happening at several temperatures, so that's not going to help us. The reaction in experiment 2 was faster because there's a greater concentration. No, 2 is not faster. And the reaction in experiment 2 is faster because the catalyst was added. That's not true. So the only good answer here is A. Experiment 1 is faster, probably because there was a catalyst added. Okay, number 14. Consider the following reaction mechanism. Step A and step B. The following potential energy graph was obtained. Okay, so we can kind of see to get over step A, that's, step 1. To get over the first hump, that's step A. To get over the second hump is step B, is step 2. So which of the following is true? The reaction is endothermic? No. Okay, endothermic. The fact that we start here, end up here, that's exothermic. So step 1 is not, answer 1 is not, B is not, A is not good. Step 1 is the slow step in the mechanism. Okay, we look here, we look at the activation energy for this step versus the activation energy for that step. Okay, this is a taller activation energy, it is a slower step. So step 1 is slower. So this is slow. Oops. This is slow. And this is faster. Okay, substance C is the transition state. No, C is an intermediate. And so C would show up down here, okay, in that little valley. So here's the reactants, here's the intermediate, and here's the products. Okay, so it'd be C down here. But the transition state actually happens up here on the top of these peaks. And so that you don't really see the transition state in the reactions. And so we can eliminate C. And the rate law is A to the 1, B to the second. Okay, the slow step is the first step, so it's going to be 1A and 1B. So it would be A to the 1, B to the 1, and that's not what they're saying. So answer B is the only good answer. Okay, for 15, assume that a reaction occurs by the mechanism given. What is the rate law? Well, the rate law is the rate law of the slow step. So we can say, okay, the rate law is going to be rate equals K times the concentration of C squared. But what happens here is C is an intermediate. If I go through and put these equations together, the C's drop out. Okay, I have 2A's plus 2B's turns into D. So I don't want C in this reaction. So I'm going to go back to my equilibrium and say K is equal to the concentration of C over the concentration of A times the concentration of B. And if I go back and say, okay, well, C then is going to be equal to K times A times B. And I'm going to go back and now take this C and substitute it in here. And we can see what we're going to happen. We're going to have K and we're going to have K. And since this is C squared, I'm going to square everything. So I'm going to have this squared and this squared and this squared. Okay, so you can see what I'm going to end up with is rate is equal to some kind of a new K times A squared and B squared, and that is answer C. It's going to be second order with A and second order with B. Okay, for the free response. Okay, real quickly here, this first equation, this is the one where we have, it's kind of a standard reaction rate, it's the method of initial rates. And we can see if we look at these first two trials, okay, that the 9 is equal to 3 squared. We can see that, when we, it's going to be a second order with respect to the SO2, okay? So like you say, if we do these guys here, that stays the same. This guy goes up by 3. This goes up by 9. So we know that's to the y squared. So second order. And for trial 1 and 2, okay, we can see what's happening is this is going to double, okay, and this is going to double. But we know if this doubles, it's squared, so it's going to be 4 times the rate. But this guy is already 4 times the rate, okay, so that means that the O2 has nothing to do with the reaction, okay. So we can write it like that, or we can go ahead and say rate is equal to K times the SO2 to the second order, and just leave out the O2 altogether. Determine the value for the rate constant. Okay, we'll just go back and take some data, throw it into the equation, solve for K, and we get this number here. Okay, part C, okay, calculate the initial rate of disappearance of SO2 in experiment 4. Okay, well, what do we have? We have the initial rate of, okay, we're trying to find this number here. Okay, well, we have a rate law, we have a value for K, we can just throw in those two numbers and get a value, and so it's just a plug and chug problem. And calculate the rate of appearance of SO3 in experiment 2. So SO3 in experiment 2, we know the rate at which the SO2 is going away. Now, what's the rate at which the SO3 is going to appear? Okay, well, they're in a 2-to-2 ratio, so it's going to be the same number. Okay, it's still going to be 6.5, so there's not a lot of calculating. 2.9 times 10 to the minus 4. What am I doing wrong? Oh, I'm looking at the wrong experiment. Okay, so we should be looking at experiment number 2, 2.9 times 10 to the minus 4. And that's where we get that. Same rate both ways. And for experiment 1, calculate the SO2 after 100 seconds. Okay, well, we just figured out that this is second order, so we have to use the second order rate equation. And now we're just going to plug and chug, and we get that answer. Okay, the following mechanisms are proposed for this reaction. Okay, so fast equilibrium in front of a slow step, slow step, slow step. Okay, so determine which one is consistent with the given data. Justify your answer. Okay, well, this one's going to be a little bit of a pain because it's got an equilibrium stuff. So I'm going to start with this one here. So this is slow step, so the rate is equal to K times SO2 squared, okay, and that actually was, if we go back to what we were doing before, that is actually the rate law, SO2 squared, okay, so that this one is consistent. Okay, if we do this one, this is going to be O2, so rate is K times O2 to the first order. Okay, well, that is not consistent because, we said it was O2 was not even in the slow step, it's 0 order. Okay, if we go back and look at this one, okay, what we're going to happen, we're going to get rid of this O, okay, because that's an intermediate in our reaction, so we're going to have to take the KEQ of the first step and then substitute in, okay, and that's going to take a bit. But the idea is we already know that the mechanism 2 is the one that's consistent with the data. Okay, and here he wrote out, if you play with it, that's what's going to come out. Okay, for the mechanism, identify the intermediates, okay, for the selected mechanism. So we're saying number 2. So what's going to happen, S2O4, that is going to be gone. Okay, so that is our intermediate, S2O4, because it's formed in one step and used up in a later step. And sketch the potential energy graph for your selected mechanism. Okay, it's a slow step and then a fast step. It's a slow step and then a fast step. And so we know that the first step here is going to have a large activation energy, and the second step is going to have a smaller activation energy. So anything that follows that is going to be okay. Now one last little piece of this, and that is if we look back to the top of the question, back here, we'll see that it says that the delta H of the reaction is negative. Okay, if the delta H is negative, that means it's exothermic, so wherever we start, we should end up lower. So we're looking for the fact that this starts high, goes low, that it has two hills because it has two steps, and that since the first step was slow, this should have been taller than this one. And that's where you get your points for this last section. And that is the practice test.